continuing with our discussion of representations, reducible representations, and irreducible representations to make life a little easier for us in both writing and speaking. We generally tend to refer to the irreducible representations by the shorter term irreps. So irreps is sort of a word that we developed for irreducible representations. So we want to look at some of the properties of irreducible representations, generically for any particular point group, and then we're going to look at the specific examples for the group C2V that we've been investigating. The symbol that we typically use for a representation, whether reducible or irreducible, is the Greek letter gamma. For the time being, we're going to assume that these are irreducible representations. And I can number the irreducible representations for a group as gamma 1, gamma 2, gamma 3, and so on. So I can number them if I like. So we can always write a generic irreducible representation as gamma with some subscript, with index, and one might be I, for example. Another that may or may not be the same we might refer to as gamma sub j. We're just being general here in a mathematical sort of way. We want to look at some of the properties of these irreducible representations. We can multiply irreducible representations, and it turns out that there's two different types of multiplication that we can do. There is cross multiplication, so we typically use the ordinary multiply sign for this. This is cross multiplication. So we want to cross multiply. And then we have a dot, and this, not surprisingly, would be dot multiplication. If you're familiar with dot and cross multiplication from linear algebra and from vectors, the ideas here are quite similar. So let's see what happens, how we define cross multiplication and how we define dot multiplication. Well, I'll show an example first. Let's assume we have two different representations in the group C2V. So let's have the first representation, and it's going to have the characters 1, 1, 1, and 1. And we recognize that that's the totally symmetric representation. And let's look at the second representation here, and it's going to have the characters 1, 1, minus 1, and minus 1. What is implied whenever we put the characters in a particular order is that they're corresponding to a particular symmetry operations. As so. So we often don't put those in there, but we know that from the character table. So if I want to do the cross product, so I want gamma 1 cross gamma 2, I can do that step by step. I look at the individual characters for a particular symmetry operation. So here 1 times 1 under E is 1, so I just bring down positive 1. For C2, 1 and 1 are the characters, so I multiply those characters. Just ordinary numerical multiplication. For sigma xz, I have 1 times minus 1, so that's going to be minus 1. And last but not least, I have 1 times minus 1 is minus 1. And we see that in this particular case, specifically, gamma 1 times gamma 2 is actually giving me back gamma 2. This is not surprising when we consider that this is the totally symmetric representation, and it's sometimes called the identity representation. And here we can see why it is so. If we cross multiply any irreducible representation, or any representation in general, times the totally symmetric representation, we get that representation back. So this gamma 1 here, the totally symmetric representation, acts very much like the multiplicative identity. So it acts like 1 for multiplication, the additive identity 0, for example, for addition. So this is how we do it. So if we multiply two representations, my result is going to be a representation again. It may or may not be one of the ones we've already seen here. Now, we know that as far as irreducible representations go, there's only as many irreducible representations as there are classes. So we know that there can only be, for the point group C2V, a total of 4 irreducible representations. Cross multiplication basically keeps working like this. There's one very special case for cross multiplication, and I want to show that one. So whenever we cross multiply two irreducible representations, we get some particular result. So I was going to call this result K here. Now, if I and J are the same representation, so they're both gamma 1 or both gamma 2, so I have it multiplied. Essentially, I'm multiplying a irreducible representation by itself. What am I going to get? Well, if these I and J are different, I just get some representation. I don't know what it is. But if so this is I not equal to J. But if I is equal to J, which means I'm multiplying an irreducible representation by itself, I'm going to get the totally symmetric representation. And in fact, this is the only way I can get the totally symmetric representation. If I multiply two irreducible representations together and I get the totally symmetric representation as the answer, the only way this could possibly have occurred is if I've multiplied a representation times itself. Later on we will use this fact. It's an extremely useful fact. Not only does a irreducible representation times itself give the totally symmetric one, that's the only way, by multiplying two irreducible representations, that I can get the totally symmetric representation as an answer, is if the two factors are identical to each other. So that's an incredibly important fact that we're going to use later on. So this is the cross multiplication, and we could cross multiply all the different representations, and it's pretty straightforward what happens. But now we want to look at the other type of multiplication, which is the dot multiplication, which is going to bear a considerable resemblance to cross multiplication with slight differences. So here we want to find out what gamma 1 dot gamma 2 is going to be. Okay? Gamma 1 dot gamma 2. And in the beginning, it works exactly the same way as cross multiplication. We go column by column, and we multiply the various entries. We multiply the characters. So here's 1 times 1 is 1. 1 times 1 is 1. 1 times minus 1 is minus 1. And then for the last class, 1 times minus 1 is minus 1. So far, we've seen that dot multiplication looks quite a bit like cross multiplication. But here's where it becomes different, in that if we were cross multiplying, we would leave this as our final result, and it's another representation. To get the dot product, I add all these values together. So I add 1 plus minus 1 plus minus 1, and I get a result that's equal to 0. So what we can say is that gamma 1 and gamma 2 in this case are orthogonal. And it's a very close relationship between this idea of particular irreducible representations being orthogonal and the ideas of vectors being orthogonal, for eigenfunctions that have different eigenvalues being orthogonal. So this orthogonality idea shows up again and again, and here we see yet another manifestation of it. And we can write a general rule. We notice that gamma 1 and gamma 2 are different, and therefore they're orthogonal. And we can write a general rule for our representations that if I do the dot product of two different irreducible representations, the answer has to be 0. So this is going to be the answer if I is not equal to j. So then the question becomes, well, what do I get if I is equal to j? So let's first put this down here. So let me talk about gamma I. So we said if I and j are different, so these makes these orthogonal because they're different. If we have gamma times j, where I is equal to j, what are we going to get? So let's see that. We can do a pretty simple version here with this. Let's erase all these, so we don't accidentally leave anything on there that was there before. And now I simply want to look at gamma. Let me do gamma 2. Maybe so gamma 2 times gamma 2. So now it works the same way that we did before, but except I only have it times itself. So I have 1 times 1, 1 times 1, minus 1 times minus 1 gives me plus 1. Minus 1 times minus 1 is plus 1 again. And because we're doing the dot product, I take these particular values and I add them together. And I see that when I do that, what I end up getting is number 4. And the big significance in this case is 4 is the order of the group. So if I multiply an irreducible representation by itself as a dot product, the result I'm going to get is going to be the order of the group. Now, using these particular facts that we have so far, that if I multiply 2 irreducible representations, I have to get another irreducible representation. If I multiply an irreducible representation by itself, if I cross-multiply, I get the totally symmetric representation. We have a technique for deriving irreducible representations for a group. So let's look at the irreducible representations that we already know about, and then we'll see if we can find, we know that there has to be a 4th irreducible representation for C2V, and we've only found 3 of them. So let's look at what these are going to be. So here is one of the irreducible representations, and we'll recall that this is the representation that corresponded to the basis function z. I'm going to judiciously leave gamma 2 here blank. Gamma 3 is the one corresponding to the basis function x, and it had the characters 1, minus 1, 1, and minus 1. And then the 4th one corresponds to the basis function y, and the characters are going to be 1, minus 1, minus 1, plus 1. So the question becomes, what are the characters for the 4th irreducible representation? By trial and error, we can work this out by multiplying the various irreducible representations. But to kind of speed this up, I'll tell you what the answer is already, that we're going to look at multiplying gamma 3 times gamma 4. So we're going to look at gamma 3. And we're doing cross multiplying here. And we want to see what characters we get for that case. So I know it's 1 times 1 is 1. Minus 1 times minus 1 is a positive 1. 1 times minus 1 is minus 1. And minus 1 times 1 is minus 1. So I have 1, 1, minus 1, and minus 1. And that is the 4th and final irreducible representation. So let's put that character 1, 1, minus 1, and minus 1. Now, it would help me a little bit in this Parse's experience, but if I look at the basis functions in a character table for C2V, I would notice that the basis function here listed is xy, and it makes sense. Since the basis function is xy, we've multiplied the result for the basis function x times the result for the basis function y, and that works out. You would also see, if you wanted to try other irreducible representations, figure, oh, well, maybe there's a 5th one somewhere. Maybe let me try xz. Well, if I multiply x times z, I would notice that I get gamma 3 back. In fact, if I multiply anything times z, because z is the totally symmetric representation, I'm merely going to get the other function back. So this allows us a technique for deriving character tables de novo, if we ever have to do it ab initio from the beginning. This is a way to do it. We try out the first of 3 Cartesian axes, and then we look for combinations of those axes, and also use the fact that when I multiply irreducible representations by each other, I am likely to get further irreducible representations if they still exist. Representations if they still exist. You will notice that if you look at the actual character tables that you find in a textbook, for example, that you do not see these gamma 1, gamma 2 labels. You'll actually see alphanumeric labels. And we're going to look at what those alphanumeric labels mean. So I will fill in the actual labels that are used in the point group C2V. Equal signs there. And you will notice that they're labeled as A1, A2, B1, and B2. So here's the significance of these particular labels. A and B are used for representations that are said to be non-degenerate. So we can recognize non-degenerate representations because in the E column, they will always have a 1. Always be a positive 1. This means that they're non-degenerate. We'll notice later on that non-degeneracy involves a single state that has a particular energy. And when we have degeneracy, we'll have more than one state that has the same energy. So this is sort of each one all by itself. We have this non-degeneracy. So we use either A or B. The significance of when we use A and we use B comes about when we look at the second column. So we notice in the second column we have our high order rotation axis, which for the point group C2V turns out to be a C2. And we notice something, that for the first two entries, the characters are positive ones, and then the second two characters are minus ones. And we notice that the plus 1 characters seem to go with the A1 and A2 representations, and the minus 1 characters seem to go with the B1 and B2 irreducible representation, the irreps. And that's exactly what this is telling us. So for a representation that is symmetric with the high order rotation axis, means that the representation has a positive character for the symmetry operation, we use the label A. If it's anti-symmetric, which means that the character is a minus 1, that tells us that we use a Mulliken label of B. So these labels are called Mulliken labels. After the scientists who developed them. So the Mulliken label for symmetric is A, for anti-symmetric is going to be B. So that accounts for the A or B part of it. So then the question becomes, why 1 and why 2? Well, part of this is we're distinguishing them from each other, so we're using different numbers. The significance of the numbering is that after we go to the high order rotation axis, then we go to the first mirror. So the first mirror that's listed in the character table, we notice that the characters alternate between 1 and minus 1. So again, this tells us whether a representation is symmetric or anti-symmetric with respect to a particular mirror plane. So we see that A1 is symmetric with respect to the mirror plane, whereas A2 is anti-symmetric. So that accounts for the 1 and the 2. The 1 is symmetric, the 2 is anti-symmetric. Similarly, for the B1 and B2 irreps, we notice that for the B1, the character for the mirror plane is positive 1, means it's symmetric, so therefore we use 1 as our subscript. For this particular irreducible representation, it is anti-symmetric with respect to the mirror. The character is a minus 1, so therefore we use the label 2. So that gives us some insight into the meanings of the various labelings that are used on character tables. So now we'd like to take a look at another character table, a character table that's slightly more complicated. And we're not going to derive all the characters for this one, but we do want to take a look at it because it shows us some things which are not immediately apparent in the C2V character table. So this is for the point group C3V. And our classic example of a C3V molecule among many is ammonia. So ammonia is a trigonal pyramidal molecule that has the point group C3V. And it turns out there are only 3 columns for C3V. That tells us that we have 3 classes. But we notice something that we haven't seen before. In the first class, we have E, which is by itself. This will always be true no matter what group we have. E is always in its own class. It's not a class by itself, so the identity is always in a class by itself. But we see that in this particular class, we have two different C3 operations. We would see later specifically it's C3 and C3 minus 1, or we can consider it C3 and C3 squared, but they form the same class. What is important about symmetry operations that are in the same class is that they have the same character. Okay, so that's going to be important. So this number 2 in front tells us how many symmetry operations we have in that particular class. In the third class, we see 3 sigma v's. That tells us that all 3 of the vertical mirrors for C3V belong to the same class, and because they belong to the same class, they have the same character. Later we'll explain in more detail how we could tell that certain symmetry elements belong in the same class, but we're not going to look at that right now. For the time being, the important feature for us is that even though in C2V each symmetry element formed its own class, which will be the case for an abelian group, in this case we have 2 and or 3 symmetry operations in the same class. But one of the nice things about the symmetry elements that all form a class, they all have the same characters. Okay. So since we have 3 classes, it tells us right away we know that we have to have 3 irreducible representations, 3 irreps, which have the Mulliken labels A1, A2, and E. Okay, and the characters are going to be 1, 1, 1. I could have written that down without knowing anything about group theory, beyond the fact that we always put the totally symmetric representation first, and all the characters for the totally symmetric representation will be 1s. So for the second, we have 1, 1, and minus 1. And then for E, so with E and E, so we have 2 different E's, which I'll explain in a second. The characters are 2, minus 1, and 0. So this is the first character table that had more than one symmetry operation in the same class. And we have 3 classes. We can figure out the order of the group. Let's just do that while we're here. So we have 1 plus 2 plus 3. So the order of the group is going to be 6. So that's a feature of the point group C3V. And we notice something going down the E column here. So here E means identity. So let me kind of just emphasize that. This is our Einheit. Spell it right. So that's our identity. That's what that E stands for. There, we notice that all our characters are 1s till we get down to here. Now we have 2. What does that mean? Well, 2 means that we have 2 states that will end up having the same energy ultimately. So that's one of the things it means. It also means that when I broke down my 3x3 matrix to reduce it, the other case is I could reduce the effect on a particular axis down to a single matrix. But recall what happens with C3V. Well, when we have C3 as a symmetry operation, this particular matrix that we used for it was minus a half, minus the square root of 3 over 2, 0. Then we have square root of 3 over 2, minus a half, and then 1. So it had a complicated matrix. But the important thing about it for us is the effect, if I just want to see what the effect on X or Y is, it's not going to work because I'm not going to get it in the form of a number times X again. So if I want to see the effect on X, it's not going to be equal to a number times X. And you'll kind of recognize that situation of having an operator act on a function to get a number times the function as being a case of an eigenfunction and an eigenvalue, or an eigenmatrix and an eigenvalue. So in this case, the effect of X and Y is combined. So the best we could do, instead of breaking it down to a single number, is the effect on X and Y would be a 2 by 2 matrix. Okay. So, and then in the case of the 2 by 2 matrix, what we use, we don't put a total 2 by 2 matrix in the character table. We're only interested in the character. And the character turns out to be simply the trace. So the trace for this, for the C3, we use minus 1, minus a half. We add those together, we get 1. So then the question might be, well, why is this a 2? Well, since we had to, the smallest matrix that we could use for X and Y for C3 was a 2 by 2, and then the Z was separate, Z works as a 1 by 1. That means for all the matrices for any representation, I have to, the smallest I can do is a 2 by 2 for x and y. So that means that when I look at the E matrix, in this particular case, if I break the E matrix down to a 2 by 2, which I have to because I had to do that for C3, now I'm interested in the character. And the character for this particular 2 by 2 matrix that acts on x and y is going to be 2. And one of the things that I haven't included before is if we look at the basis functions for this particular irreducible representation, I see that I get this notation of parentheses x comma y parentheses. Now that looks quite a bit like how we write an ordered pair in Riemann two-space, so a two-dimensional Cartesian coordinate system. We would often write it that way. That's not what it means. What it means in a group theory context is that x and y are interrelated to each other. So we actually have a doubly degenerate representation here. It's because both two different functions are interrelated, and those interrelated functions will end up being degenerate. They have the same energy at some point. So the way we recognize that, among other things, is we notice that the character here is a 2. So what this E means is, this is a Mulliken label. E up here is a symmetry operation of the group. Here it's a Mulliken label, and E is the Mulliken label which we use, even though it's confusing, for a doubly degenerate representation. So kind of make a notation here of things that we know about Mulliken labels. We know that A and B are for non-degenerate. We use E for doubly degenerate. That's 2. I won't write degenerate again, but you get the idea. And then if we have a case where we have a triply degenerate situation, we use the much more logical T for triply degenerate. So this type of notation is going to be used quite a bit. As we get to more three-dimensional list molecules, so things like the tetrahedron and the octahedron, these E and T irreducible representations become increasingly important. So admittedly it is confusing that we're using E to mean 2 completely different things, but that's one thing we have to get used to. And then T makes a little bit more sense of why that's going to be the Mulliken label for a triply degenerate representation. And then the last thing we double check is, kind of highlight this point, is since we have 3 classes, we have 3 irreducible representations. The basis function for this one would be Z. I'm not going to write the basis functions for A2 because there are additional complications which ensue to those. But the important thing is to see at least somewhat of where this comes from. And the most important thing is to be able to recognize that if we see a character of this type, where character is 2 in the E column, that's going to tell us that we have a doubly degenerate representation. If we see a 3 here, it's going to be a triply degenerate representation, and those doubly and triply degenerate representations are going to become incredibly important. You are already familiar with cases of triple degeneracy. For example, the 2p orbitals of carbon have the same energy, at least in the atomic state, so they're triply degenerate. The d orbitals for an atom, so the 3d orbitals, are 5-fold degenerate. So you have 5 different orbitals with exactly the same energy. The f orbitals are 7-fold degenerate. So we can have multiple levels of degeneracy beyond 1, which is non-degenerate, 2, and 3. We have cases with which we are already familiar of more complex degeneracy. Cases with which we are already familiar of more complex degeneracy.